So what this facility will do will make the equivalent of 100 million gallons per day of product, which is about 450 megaliters a day. And we will put a portion of that water in a series of spreading ponds or lakes and allow the water to naturally percolate by gravity and replenish the aquifer. And then a small portion of the water will actually be injected along the coast, very close to the Pacific Ocean, and create a seawater intrusion barrier, or what we call a hydraulic barrier, to prevent the intrusion of seawater into the local groundwater aquifer. In Southern California especially, the groundwater aquifer is geographically connected to the ocean because of fault lines. You know, we're in a frequent seismic area, so there's a lot of fault lines that connect the ocean directly to the coastal aquifers. And the coastal aquifers are the main source of drinking water for most of the population in Southern California that lives along the coast, which is a majority of Southern California because everybody wants to live near the coast. So what you're seeing here is the first step of the treatment process, microfiltration. So this is the hollow fiber membrane technology. This is from a company called Memcor, recently purchased by DuPont Water Solutions, part of the DuPont family now. And this is the exact membrane that we're using in this process. So this is a submersible, or what they call a vacuum-driven system. So when you look inside each of these basins, we have 684 individual membranes inside each basin. The basin's fed with the treated wastewater from a large wastewater treatment plant located next door. We add a little bit of a chloramine residual to the water, and then this membrane directly filters down to, these are polypropylene, so these are 0.2 micrometers pore size. So what we're hoping to do with this process is remove the suspended solids, the bacteria, the larger particles, to polish the water, so to speak, for our next treatment step, which is our main treatment step, the reverse osmosis, which we'll see after this. So in this one, you'll hear often the sound right now is these are backwash every 20 minutes. So you're hearing the aeration step, you're hearing the reverse flushing step. So the way this one works, I think most of you may know, but the way the microfiltration works is the fiber actually has got a hollow center, kind of like a drinking water straw, and then the walls of the fiber, which is like the walls of a drinking water straw, they have microscopic holes, the 0.2 micrometer holes. So we're pulling a vacuum or a suction with a pump and forcing water to go through the side wall of the fiber and accumulate in the hollow center. And then when it's time to do the self-cleaning of the backwash, what we'll do is we'll bring water the opposite direction, previously filtered or clean water, through the hollow center and force it through the sidewall to hopefully remove the fouling layer, while at the same time agitating or vibrating the fiber with compressed air to try to remove the fouling. Over time though, even the backwashing doesn't keep the fiber clean, so then we do a full chemical cleaning, and that's why you'll see a series of cleaning tanks. So we clean this fiber with a low pH, pH 3 citric acid, and then we clean it with caustic or high pH sodium hydroxide to remove the foulant layer and then put it back into service. So these require a cleaning every 3 weeks and a backwash every 20 minutes. And we get about 90% recovery because of that from this process. So all of the waste, the spent backwash water, the used or spent cleaning solution, all gets recycled back to the main wastewater treatment. So that part is recycled in a partnership. And then after this process, which we'll see after, the water will actually then go to 2 more treatment steps. The reverse osmosis, which is the main treatment step to remove the organics, the dissolved contaminants, specialty salts, and then emerging contaminants. And then after that, everything will go through an advanced oxidation process with high amounts of UV light and hydrogen peroxide residual, which we'll also see. So the way this plant is kind of set up, everything comes here by gravity. That's why these basins are so deep underground. So there's 36 of these individual basins, and each basin can produce about 5 million gallons a day of product water. And you'll see the construction going on as we walk. We're actually expanding the plant from 100 million gallons a day to 130 million gallons a day. And this construction will be done in 2 months. We're almost done. It's been 3 years. So when that's done, and we can make 130 million gallons a day, we are adding 12 more of these basins. That's where the construction's going on. So the way this plant is configured, all of the equipment, the pumps, the piping, the electrical, everything is underground in a basement, so that these basins can be low to the ground and be fed by gravity. The hydraulics work better that way. And then everything being in the basement protects the equipment, but also keeps the sound down, because this plant is surrounded by homes on 3 sides, and on the 4th side is the wastewater treatment plant. So everything has to kind of fit into the neighborhood without having excess noise or odors or anything else. So if you follow me, we'll go downstairs briefly. You'll see the basement. We'll walk through it, and then we'll walk back up and head over to the next process. So I assume everybody can do stairs. If there's any issues, let me know. Okay. Like we talked about above, we're now in the basement, so this is where all of the equipment and all of the components that make the system work. The individual basins have their own large pump, 60 horsepower pump. That's the pump that draws the suction that allows all the water to come into all those individual fibers inside the microfiltration membrane or each filter element. So because we have so many membranes in one basin, we have to have a fairly large pump. Everything's computer controlled, so the program determines when it's time to go into the filtration cycle, when it's time to go into the backwashing cycle, when it's time to do a cleaning cycle. With the operators are the ones that intervene in terms of determining whether it's time to run the cleaning process or not. Everything on the wall in front of me or behind all of you, that's all of the chemicals I was talking about. So all the chemical is pumped in from a separate facility. You see caustic, citric written stenciled on the piping. That's for the clean in place step, the low pH solution, the high pH solution. And so everything in here that you see is, this was all built as part of the original construction, so in 2008. And then in 2015, we did our first plant expansion. And, we'll go by there, but you'll kind of see down at the end where it's much brighter. That was the new portion that was built. So the project was always designed that as there needed to be more sources of water to replenish the groundwater aquifer, that the plant was designed as such to allow for more modular equipment to be added and expansion to be included. So now the construction that we're under, where we want to expand the plant from 100 million gallons a day capacity to 130, then we'll have built out all of the space that we have, all the capacity we have. But what we most like to point out is once we are at 130 million gallons a day, we'll be taking all of the wastewater that's produced in this area and reclaiming it as reclaimable. So there's no more to take after this, which is good. And you may see this in other parts of the U.S., but the big thing that we're finding in the southwestern U.S. is because of the drought, where we're not getting very much rain, we don't have a lot of natural water and precipitation, the wastewater flows are dropping too. And because people are conserving more, the wastewater flows are dropping, so there's less for us to reclaim. So we're trying to operate all of our processes at higher and higher recovery to get as much production as we can, because the feed water supply continues to drop with the drought. Hopefully it won't drop anymore, because we've already committed to building this expansion, but I think in the end we'll be okay. So if you follow me, I'll kind of walk slowly through the basement. Feel free to take pictures, look around. You'll kind of hear noises down here as well. Because this is what we call a batch process, where each individual basin is constantly in a different mode of filtering, backwashing, cleaning. Everything is run by compressed air pneumatic valves, so you'll hear a lot of hissing and air sounds. To run all of these valves, there's a big extensive blower system as well. That's kind of the noise you hear in the background that runs all the valves. and then there's a whole series of large blowers that run that aeration step. All of that is housed down here, so that's the noise we'll be hearing as we walk. And then we'll walk up another set of stairs and make our way over to reverse osmosis. So feel free to take pictures along the way, or if you have any questions, feel free to ask us. Also, when we're done, you'd see the poster there. When we're done, the hope is that when we finish the final expansion at the end of this year to be at 130 million gallons a day capacity, that's enough water for 1 million people in our 2.5 million person service area. Right now, we make enough water for about 850,000 people just using the highly treated recycled water. We still also have imported water that we can use to replenish the aquifer, and we still can use our local Santa Ana River water, which is a local river that runs through this area, and Orange County Water District has the rights to that water. But like everything else in Southern California, that local river supply is at all-time lows. For 25 years, it hasn't been this low. So this project is really what is helping us overcome the drought that is affecting our other supplies. This is allowing us to continue to allow people to use roughly the same amount of water they did even 5 years ago and still sustain the groundwater aquifer without overdrafting it or making the groundwater aquifer unsustainable like it is in other parts of California where they've overdrawn the aquifer and they get subsidence or land settling. We don't have those issues here. So if you follow me, we'll walk up the steps and head over to the reverse osmosis. Make our way over to RO. These are all the cleaning chemicals I was talking about. They all are stored here and then they're pumped down into the basement by the computer system every time the membrane requires a cleaning step. So this is the caustic here, sodium hydroxide, citric acid, and then at the end there's a little proprietary surfactant that we also use during the caustic step. And then if you look across the road, the building across the road there with the kind of stripes on it or vertical lines, that's the Orange County Sanitation District. That's the main wastewater treatment plant for this same part of Orange County. So all the raw sewage goes there. It goes through secondary treatment. Then we receive their secondary effluent wastewater. And we have a partnership. That's why we built the facility right next to each other. So we're right next to the wastewater treatment plant. And that structure there with the stripes that you see, if you know about wastewater treatment, that's the primary clarifier. That's actually where we put the spent backwash waste.
저기 하수 처리장. 저 물 받았어요. 여기 처리.
아, 여기 들어오는 물이요?
저쪽은 하수 처리하고.
아, 뒤쪽에요?
저 벽 뒤에.
네.
그 하수 처리한 물을 여기 받아가지고 먹는 물 수준.
아,
저 앞쪽이 이제 리버스에서 마시는 역삼투.
어디요?
저 앞쪽이 역삼투
아,
시스템인데
역삼투.
세계에서 제일 큰 시스템이에요.
아,
그러면 이제 물을 먹는 물 수준보다 더 깨끗하게 처리해 주는 거예요. 이걸 하려고 하면은
네.
약품 세척하는 약품이 필요하니까
네.
그 약품 저장 탱크 있죠.
아, 약품 저장 탱크.
RO 피드 있지.
네?
RO 피드라고 돼 있죠. 피드.
네.
피드가 이제 밥이라는 뜻인데
아, 피드.
마이크로 필터에서 거친 걸 이렇게 해서 RO 피드. 총 에너지 55%를 여기서 다 쓴대.
아, 총 에너지 55%를 역삼투 한 곳으로 들어가 보도록 하겠습니다.
이게 지금 역삼투 그 모듈이에요. 한 모듈.
역삼투의 한 모듈.
이게 이제 쭉 이렇게 있는 걸 트레인이라고 그러고
아, 쭉 있는 걸 프레임.
한 개 한 개가 이제 모듈이고 그다음에 이게 모아져서 물을 이렇게 다 뽑을 수 있도록.
Obviously, wastewater is natural salty, in our case, about 1,000 milligrams per liter of salt. We want to remove that below 500, at least we get closer to 20 milligrams per liter. But mainly, we want to reduce the dissolved organics. In our case, they are regulations are in California, we have to reduce the total organic carbon below 0.5 milligrams per liter. And we really can't do that with anything other than reverse osmosis that will fit in such a small footprint. So that's why we've invested a lot of time and energy into making RO, or reverse osmosis, work. What you see here kind of on my right, this was the original RO built in 2008. And there's 15 individual trains, or you'll see groups of white vessels together. Each one does 5 million gallons a day. So there's 15 over here. And we added 6 more on this side in 2015. We expanded the plant. And then just got built about a month ago. That's our final expansion. So when we're done in this building, we'll have 27 individual RO trains, and each one can produce 5 million gallons a day. So this is by far the largest RO you'll see in the Western Hemisphere. There's a few bigger in the Middle East, and a few others as well, but definitely the biggest doing water reuse. So that's what kind of makes this plant special. If you know about reverse osmosis, you know the pressure requirement is high, but you also get a much finer level of filtration. So when we were at the first treatment step, we saw those horizontal pumps in the basement. They were about 60 horsepower. In this case, in order to make the same amount of water, instead of the pore size being 0.2 micrometer, now we're talking thousands of times smaller than that. So now we use, if you remember your chemistry, we use molecular weight cutoff. So basically anything about 150 daltons or less is what will make it through this process. So the pump now, because of that, this is a 1,000 horsepower pump. So we went from 60 horsepower in the first process to 1,000 horsepower because of the finer level of filtration we're trying to accomplish. And in that first process, those pumps basically operate between about 3 psi when they're clean and 12 psi when the membrane's dirty. So very low pressure. Here we operate about 150 psi when the water's clean, or the membrane's clean, and 250 psi when the membrane starts to get foul. And we clean these once a year using a roughly the same as microfiltration, but basically a proprietary surfactant at high pH, and really letting that water recirculate to soak through the membrane. That removes the foulant. In this case, it's mostly biological fouling is what we're worried about. We don't get a lot of mineral scale because we use a proprietary anti-scalant. That's some of the chemical you see over there. So we can keep the minerals in solution, the ones that want to scale. This process operates at 85% recovery. So we still do generate 15% waste, usually called brine or concentrate. We actually discharge that into the Pacific Ocean, along with other treated wastewater from the treatment plant next door. They have an ocean outfall where their treated wastewater that isn't used by us is disposed of in a 5-mile ocean outfall. So 5 miles out into the ocean, about 18 kilometers out is where the wastewater is discharged, about 100 meters deep into the ocean. So that's pretty typical in Southern California. The big wastewater plants, they're not sending the flows to be recycled like they are here, and then they're put for ocean disposal. So as we go towards the back, I'll stop real quick. You'll see kind of a full-size membrane and one cut open if you've never seen what the inside of a RO membrane looks like.
So what is that? A membrane?
So this is a cartridge filter. That's a cartridge filter.
Oh, cartridge.
So that's kind of the pre-treatment before the RO. That's why it's so small. So here's an RO membrane been cut open. So this is what a full-size one looks like. They look the same whether it's in a seawater desalination plant or like us doing wastewater reclamation. This is one if a portion's cut out. This is if you take the fiberglass housing off and unwind it. What's inside is the membrane is actually the white sheet here in the center. So the way the reverse osmosis works is there's a sheet of membrane, which is this. There's a spacer material, and then another sheet of membrane, and it's glued on 3 sides, kind of like an envelope. And then the fourth side is connected to a slotted or a PVC pipe with holes in it, which is called the carrier pipe or the permeate pipe. And what we're trying to do is we'll take 25 of these membrane envelopes, roll them up, put a fiberglass housing on it, and then put a feeder on the end. And so the hope is that when the water is fed from the end, it'll make its way into one of these membranes, get to the spacer in the center, and spiral all the way to the center and get collected in the center pipe. That's why the center pipe has holes. Anything that can't make it through one of these layers travels tangential or parallel, comes to the other side, goes into the next membrane. So each of our vessels has 7 of these membranes back to back. And then in order for us to get the recovery very high, we stage it so that it goes through 3 stages of membrane in each train. That's what allows us to get to 85% recovery. So the water that goes through one set of membranes is collected, the clean water. The reject goes through another set of membranes to get additional clean water, and then the reject from the second set goes through a third set and collect the clean water along the way. That's how we get to 85% recovery. So that's what these look like. Rare you see them, and you remember before, this is what the microfiltration, the first step, looked like. So both made out of similar material, but obviously much finer level of filtration here because we're trying to demineralize and remove dissolved organics in this step. Yeah, so Nitto-Danko is one of our suppliers in the U.S. They go under the Hydronautics name, but
RO?
RO, yeah. So 2 of the biggest RO manufacturers are based in Japan. Toray and Nitto-Danko are the 2 biggest. And then the third biggest is DuPont, Film Tech, but they're based in the United States, in Minnesota.
Which one is best?
Film Tech. It wasn't DuPont before. It used to be part of the Dow Chemical Company, and then it got bought by DuPont. That's the one we find works the best. But the Toray product's good. The Nitto-Danko product's still good too. And there's others. Suez makes a membrane as well. But these are kind of the main ones that work in the wastewater reclamation and seawater desalination. All right, so if you follow me out the door here, we'll take a look at the last step, the UV advanced oxidation, and then we'll have a chance to taste the water that's produced. So there's a good kind of little diagram here, but if you're not familiar with it, the ultraviolet light is basically very similar to a lamp you would see, fluorescent lamps that you see in office buildings and the ceiling. The main difference between those and the ones we use is this has a special coating so that we target a certain wavelength of light. We're trying to get around, if you remember from your chemistry or your physics days, 228 nanometer wavelength of light is what we're trying to target coming out of the lamp. We want to get the UVA and UVB spectrum of rays, similar to what you would find like in disinfection systems in large aquarium systems where you can't use chlorine, or if you like a tanning bed, the same kind of lamp you'd use in a tanning bed. You know, if you get a tan, that's why you have to cover your eyes because it damages the cornea. So what this system's set up is the lamp sits in a cord sleeve that transmits the light without blocking it. And what you see behind me are 3 large vessels. So the water comes through the bottom vessel, comes through the second vessel, and then comes through the third vessel, kind of in a serpentine path, or goes through 3 stages of lamps. There's 144 lamps in each vessel. So there's a total of 432 lamps that irradiate the water. And prior to the water coming into the UV system, we dose with 3 milligrams per liter hydrogen peroxide. So the hope is that the high amounts of UV light with the hydrogen peroxide will generate hydroxyl radicals or OH ions so that we can further break down organics, because there are small, low molecular weight organics that will also pass through RO, and we need to remove them as well, and that's what we rely on for the advanced oxidation process. In addition, because we're using so much UV light, it acts as a secondary disinfection step. But the viruses, the bacteria, and other pathogens should have been easily removed by the first 2 membrane processes, but our regulations require a redundancy or an additional disinfection step in case there's any process issues with the first 2. So this serves 2 purposes. It serves a redundant disinfection step, and then it functions as our primary low molecular weight organic removal step or oxidative step. So if you follow me this way, we'll show you a little sink of what the water looks like after microfiltration and after RO and UVA protected by the RO. So here, face the sink over here. The middle sink, the way to think of it is the middle sink is what went into the RO process, so that's after microfiltration. The sink over here is after microfiltration, reverse osmosis, and UV advanced oxidation. The sink on the end is the concentrate or the reject from the RO, which is sent to the ocean outfall for disposal.
여기
So
농축수,
the middle sink, which is after microfiltration, that's suitable, especially in California and most of the U.S. That's why we go to the trouble of going through reverse osmosis, advanced oxidation. So the only thing that this water doesn't have is at the end of the process, we do add minerals back in because if you remember after reverse osmosis, it's got low alkalinity, it's got low buffering capacity, so we want to raise the pH and the alkalinity. And the way that we do that is we add calcium hydroxide or hydrated lime, bring the pH up, try to get a slightly positive saturation index, get the pH, right now it's around 6, get it up to 9 when we're done. So this is the one that we're gonna try. So we have, go first. So we have cups over here, and you'll see there's a slogan in English on the cups that says, it tastes like water, because the number one comment we would get from visitors is, oh, it tastes like water. They expected it would taste like something else because it started out as wastewater, but all water's water, right? You know.
like area.
Yeah.
나는 말이죠. 이게 RO 공법 리버스 오스모시스 프로세스 과정이고 이게 마이크로 필터레이션 과정, 이게 UV로 얘는 골프장까지.
Alright, so if you guys want to follow me back, we'll go this way, work our way back to the front, and if you have questions along the way, feel free to continue asking. There's a trash can here for your cup, or feel free to keep the cup.